So, what were we talking? The cover of Science. It's actually very interesting to take a look at this and see what the problems are and whether or not this is really working as a description of what this is about. What were you saying, Tom? That
Well, I've always thought that is a spectacular graphic, and it has a lot of positive aspects about it, conveying what we are thinking about when we talk about Bose-Einstein condensation. But it also has the possibility for some misconceptions. I'm not sure whether we should start with the misconceptions. I think we just did, so why don't we take off on that? That's indicated as being the molecule of the year, and in a way that's a joke, because the Bose condensate is certainly not a molecule. But there's a misconception, possible misconception there, because a previous molecule of the year was C60, which was a molecule composed of identical atoms, carbons.
I'm sorry?
And also, this is a crystalline array.
Right. In C60, there's a geometrical array. And if you look at this, you see immediately a geometrical array. And you say, oh, maybe in the Bose condensate there is spatial order. And that's a misconception because there is no spatial order there in the way that there is in C60.
Right. Well, these are the difficulties for people like me who are coming on this pretty much for the first time, and the grasping this notion of quantum states as opposed to the states that we're somewhat more familiar with, atomic states, if I could say it that way. It's extremely difficult for us to truly grasp it, and I don't even know if we're able to without the mathematics. That's something that I would be interested in your take on. Whether
I think you can. I think he's done a very good job of doing that. But the words of the things are a problem. It's the condensate idea that is strange.
Yes.
Because it is a condensate, but not in space.
That's right.
It's a condensate of his kind. I would like to follow your simplicity and say it's a condensate in wavelength space, which represents the wave nature of the atoms that make it up, just as the position in ordinary space represents the particle nature. And because this is a mixture of the two, we've got to have that point of view.
But you have to be careful with that, too, because condensate in, say, wave vector space makes you think it's going into a given momentum state, a given wave vector. And if you're in a trap, that's not true either. Because here...
Well, the range is smaller.
That's true. Here you're condensing into a quantum mechanical state, the ground state.
Yes.
And what people don't understand is that in a quantum mechanical state, there is not a single position. There is not a single velocity. But there's a distribution of positions. For example, the 1s, the electron in a hydrogen atom, in the chemistry textbooks for high school, you see a cloud of position.
Right.
And that gets across to the student at least the idea that position isn't certain.
Yes.
In the trap, the same thing is true of the velocities. The velocities have a distribution, sort of a cloud of velocities.
But I would call them wavelengths.
But a distribution of them.
Yes. A spread of wavelengths. Yes.
Can we talk about...
Distribution is probably not a good word, but I don't know.
Can we talk about a wave? Can we start there? Do you think that's a good place to start? Do you think we...
We could. I'd like to come back to the cover because Wolfgang was telling me about a very interesting interpretation of that on the positive side when you were talking to a group of people.
Yeah, when I've shown this cover to many lay people, and I think it conveyed something to them. It's sort of the question how you address it, whether you want to convey that this is like a crystallized structure. But my take on it is that these guys are all identical and they could be anywhere. It's not that we mean they are localized, it's a group of people which is sort of smeared out over this region. And those people have lost their identity, they are faceless, they march in lockstep. So for me this represents how I describe Bose condensates as many meta waves oscillating in concert. And this is sort of what you associate, many people marching in lockstep. That's what exactly Bose condensation is about, many atoms marching in lockstep.
I think the key word is loss of individuality.
Which I think is
in
not clear.
Yes,
It is
that's
not clear here.
Oh, I think it is. I mean, the colors, all the colors have now become the same.
I see, but I see individual
mm-hmm.
pieces. That's the part that, for me, has gotten in the way.
An army of soldiers where everybody looks the same. There is no individual
Okay.
nature in
Well,
it.
then we need the words then. See, that's
There's a drawing in that slideshow that has maybe 4 steps of change, ending at one point just having waves mixed.
Let's see.
This is it. Yes, yes. I
Let
think
me-
this
let
is a
me-
wonderful image.
Let me see. I think we're
If you talk about that in relation to this,
Those two
think-
together, I think,
yeah.
complement each other.
This is a little cleaner, I think. Do you want to just go through that, perhaps? It could be helpful for us.
This is exactly the 2 spaces that I was talking about, put done better.
Yeah.
Yeah.
Uh,
What do you
yeah.
think?
I mean, I think what we are facing here is the misconception between crystalline structure and atoms being smeared out. And I've also seen that in the public, among journalists, it became quite popular to say the Bose condensate is a state where many atoms merge into a superatom. And I always felt that this was a very dangerous phrase. If by superatom you mean that many atoms are just in one state and are one entity, this is okay. But many people would associate with superatom what you were referring to, like a supermolecule, something which is really a different kind of entity.
Right.
But my take is rather the Bose condensate should be more described by matter waves oscillating in concert. And if you want to go one step further in depicting it, it would be atoms marching in lockstep. But it is the same atom, it's the same atom we put in, but those atoms now march in lockstep. It's not that the atomic nature has changed, it's not that atoms have fused into a bigger entity, it's more this quantum coherence, this marching in lockstep, which distinguishes the Bose-condensed state.
But the lockstep is with their paces, not with their position on the surface.
Footprints.
Yes, yes.
And what
You're
get
right.
and what gets them into this lockstep?
Nature.
That's the way it is.
That's just the way.
There
Yeah.
are 2 kinds of things. Those that don't do that, and those that do that.
Well, there's a phase transition which separates. It's really a qualitative difference between these 2 states of matter. And the interesting thing is that there are many phase transitions in nature. The simplest one is the freezing of water. Another more esoteric one is the lining up of all the magnetic moments to form a magnetic bar of iron, for example. All other phase transitions in nature, every single one of them, is mediated by an interaction between the particles, an interaction between the spins, interaction between the water molecules. This one, there are no there don't have to be interactions. This would take place even if there were no interactions, if these atoms could just pass right through each other, not even a hard sphere radius. Now, there is a weak interaction, but it turns out that this transition does not depend on that interaction to take place. That's one of the reasons that physicists, I think, are so excited about this transition.
Do you?
That's also why it could have been found out before there was even quantum mechanics.
Yeah.
It was found out by using that simple principle of the
It's a
phase
matter,
space
it's a
and the
matter of
kinds of spaces.
statistical mechanics. that's
Condensation,
right.
yes. This
It's
is
just the
mechanics,
statistical mechanics.
which brought in this 2 ways.
And this is where the problem is for lay people as myself to understand that even the notion of statistical quantum mechanics is extremely difficult for someone like me to grasp. We have to think completely differently, don't we? Where do we even begin? I mean, this is not a fair question to just throw at you, but is there a place? I mean, even repeat ourselves a little bit, perhaps. Where can we start? Where can someone like myself start thinking about a quantum mechanical state? Do I have to erase something from my head to begin? Is it about erasing a discrete particle? Do we have to stop thinking about things being discrete? Or
Maybe it's a little more sophisticated than that. You have to stop thinking about the possibility of following a particle along a trajectory. So if there's one major difference that I think of between a classical system and a quantum mechanical system is that classically you can imagine following a particle along a trajectory. It has a velocity, it moves. You can't do that in quantum mechanics. Because if you do find out, if you determine that it's in one place and going in a given direction, then you completely change the nature of the system afterwards. The particle does have a distribution of positions and has a distribution of momenta. So if you make a measurement, you'll get a result. But you have to think about the system in terms of possessing a distribution, both of positions and velocities, say.
But I think we have some access to this reality if you think in terms of waves. I mean, we've all seen water waves. And this is what is depicted here, that, I mean, the picture we have to break with is the picture in the first panel, namely that particles have position and velocity.
Yeah.
Right.
But if we sort of add on that particles are not at a given position and have a certain velocity, they are rather quantum-mechanically smeared out. They are, I often say atoms are not hard billiard balls, they are fuzzy objects. But this is just a way to circumscribe
Somehow.
that they are, it's not that the atom itself is fuzzy, we just don't know where it is. And so therefore, my knowledge where the atom is fuzzy. So therefore, without explaining exactly what it means, you would use the language of quantum mechanics and the mathematical description. I just would convey that atoms are kind of fuzzy objects, they are sort of smeared out. And this is what we call a wave packet in our language.
I think the use of the word wave is wonderful and indispensable and should really be at the basis of what you mean by quantum mechanical
So an
solution.
atom is a wave, period.
Period.
Is also a wave.
And the wave
also
is,
a wave.
and the wave is characterized by a certain wavelength.
I think that's
And the wavelength determines also what is the extension of the wave packet. So my understanding is that atoms are kind of fuzzy, but when we extract energy from the system, when we classically slow the atoms down, this means in the wave picture that the waves, the wavelengths gets longer and longer, or the fuzziness of the atoms increase. And if we continue this cooling, the atoms get fuzzier and fuzzier, and neighboring atoms start to touch each other, start to overlap. Oh, this is very nice
This
to
is
show
a-
here. Then the atoms overlap, and then all those waves start to oscillate in concert. They just synchronize.
A third step would be nice here.
Right, right. One problem with the wave pictures, when someone thinks of a wave, they think about a very definite wavelength.
Yes.
In this particular case, there is a characteristic distance which one uses instead. It's called the thermal de Broglie wavelength, and it's sort of an average wavelength. But it can also be looked at as a characteristic length, and that's what I've tried to indicate in this diagram. That the characteristic length is sort of an average over all the wavelengths associated with a quantum mechanical particle. But it does give you a physical distance scale. At high temperatures, that distance scale is extremely small, and it can be actually smaller than the actual physical extent of the atom itself. On the other hand, as you cool it down, this extent grows. And really what it is the region over which the particle is felt statistically, not the range over which you feel its real force, but the range over which its presence is made known through statistical mechanics. So here, the little red dot would be the hard sphere radius. It's the region of force. But now the de Broglie wavelength, this characteristic length, can become so large that the particles are very far apart compared to their characteristic size, hard sphere-wise, force-wise. But they are all overlapping. They are all feeling each other's presence statistically. And that's what I was trying to get across there. But you're right, Phyllis, that an intermediate
An intermediate step would help. Also, I think it would help if there were a haze over the hard red
Yes.
bar
Yes.
too,
It's-
so that there's a sense of the
The ho-
three-dimensionality.
Yes.
of the
In fact, one of
situation.
the problem, again, coming as a non-scientist, when I see drawings of electromagnetic fields, well, you know, it's, and I'm awful at this, of course, but yes, let's get that out. you would, well, I don't know if this is even close to whatever. Maybe you could do better. Yes. Uh-huh. Or just some sort of things like that. Is that not really? But when you're describing electromagnetism and fields, it seems as if when you draw the line, that's the place where something exists,
Yes.
and the empty space between it indicates that nothing exists. And that's not quite exactly what it's about, is it? But that's something that you all accept as protocol of some sort.
But this is just the
these are-
same as if you have a topological map. The map has certain contour lines, but it doesn't mean that there is, no landscape,
But
no
that-
box between.
right.
You just indicate with certain lines what is characteristic for the distribution.
But that's coming with a knowledge. We're kind of talking about people coming without any sort of knowledge, and probably that's not who we're talking to in this conversation. But there's a somewhat of a counterintuitive feeling when somebody's not used to working with these kinds of things, to understand that there's a gradient of some, or is that the right word, gradient? Yeah. And
Coming
that,
back to trying to understand the Bose condensate,
yeah.
I was trying to think of it in terms of misconceptions. And there's another misconception, I think, that keeps many people in the public from understanding just what it is that we're doing. Because one of the things that students seem to leave high school with is the concept that absolute zero is the place where all matter comes to rest. All motion stops. But now we're talking about a Bose-Einstein condensate, which is near or almost at absolute zero, yet we talk about motion, we talk about
Yes.
velocity. The fact of the matter is that at absolute zero, particles do not come to rest. The true statement is that at absolute zero you can no longer extract any energy from the system without destroying it. And that's quite different. But take as an example the electron moving around the nucleus of a hydrogen atom. It's in its ground state, it's at absolute zero, yet if you make a measurement of the velocity, you'll get a result. If you make that measurement again and again and again, you get a distribution of results because there's no one velocity associated with it, but there's certainly a kinetic energy. It is, in the best sense of the word, moving, even though it's at absolute zero. So coming back to the Bose condensate, they would think, oh, well, why aren't they all at rest?
Also, the condensate word is such a
Yes.
slightly troubling one because it implies a high density.
But let's first maybe stick to, I think Tom's aspect should maybe be a little bit further elaborated. And one thing is, I think many people have heard about Heisenberg's uncertainty relation. So if you just say, take one of those pictures and say, look, this is the condensate. The condensate is extended over a certain region, which you might call delta X. And then people know that there's a Heisenberg's uncertainty relation, which says that if delta X is the uncertainty in position, there is an associated uncertainty in momentum.
Right.
And if there's a momentum uncertainty, it means there is zero-point motion, there is some quantum mechanical motion associated with that system.
That's a nice way of getting to it without doing any mathematics.
Yes.
Just the concept of the Heisenberg uncertainty
Yes.
principle then allows you to explain the motion at zero temperature.
The
or in the ground state.
velocity can only be sharp zero when the object has infinite extent. If it has infinite position uncertainty, then momentum can be sharp and can be zero. But as long as we are talking about finite size objects, and this is what the experimental Bose condensates are about, they are millimeter or sub-millimeter lengths. With that, there is a momentum uncertainty associated, and
Okay.
that means motion, that means zero-point motion.
And that's related to temperature? No.
No, it's just that
Okay. Because I thought I remembered was that movement is related to when atoms move quickly, the temperature is high.
Well,
Is that
that's-
not right?
No, that is true. It's just that there are two different contributions to the motion of the atom. One is the contribution having to do with the Heisenberg uncertainty principle. The other is the fact that if you're at a high enough temperature that you can start talking about the position, if you can use this image, then there is a thermal contribution to the motion as well. And there
Okay.
it is true that the kinetic energy is directly related to the temperature. In fact, in both of our experiments, in the gas, the portion of the gas that has not condensed, we measure the temperature by measuring the distribution of velocity, so the distribution of momentum. So we use that as a, but when they go into the condensate, as far as temperature is concerned, it's as though they were at zero temperature. And then the contribution to the distribution of velocities is only quantum mechanical, and
Okay.
only determined by the Heisenberg uncertainty principle.
I mean, it's a subtle point. If I give
Let's do this.
a simple popular talk, I usually say temperature is just energy. Temperature is a way how we measure energy. And then I immediately try to demystify that some people have the notion that the absolute zero can never be reached. I mean, this is true and this is false. And I sometimes compare it to, can you reach absolute zero pressure? That depends. I mean, if you suck out of a chamber, you suck out the air, and you have very good pumps, you can reduce the pressure to smaller and smaller values. But there are always a few atoms and molecules left, so the pressure is never rigorously zero. But it's clear the harder you suck, the harder you pump, the closer you come to a completely empty chamber. And temperature means for our physical systems that they are empty of energy. We have sucked out, we have extracted all the energy. So there is no mystery about
Yeah.
absolute zero. It just means we remove the energy from the system. So therefore, temperature is just a measure of energy. But now when we talk about the zero-point energy and more general forms of energy, we have to be a little bit careful, because then temperature is not associated to the total energy, but to the energy which can still be extracted from the system. And it would also lead us to connect temperature not to energy, but to an energy distribution. You know, if a bullet moves, it moves fast, it has energy, but the bullet might be cold. So the motional energy is something we would disregard. We are just looking for the internal energy of the bullet when we use the word temperature. So one has to be careful. You can go very far by just setting temperature and energy equal, and you can convey a lot of basic concepts, but you find your limits at some point.
Yes.
But if what you're thinking is how to reach a wider audience, then to talk about energy and temperature together makes it more than twice as hard, because those are each hard things, and for people who haven't thought it through. So it's a case where you make it harder by making that comparison.
Is there a way that you would prefer to draw a picture of temperature, for example, to show what happens when things get cooler?
There is one. He drew it, a very nice little one, very truncated to this particular discussion, but
Yes.
it's the one where he shows the states
This-
in a box, in a
Yes.
row. And some, no.
No.
Another much more technically looking one, but very
Okay.
clear.
Was it on the?
No, I believe it's.
okay,
probably one
let's-
of-
let's see.
Unless you had printed
This
it.
one.
Oh, yes, this is a wonderful one.
Could we?
A few more of those would be
Okay, that would be great.
ideal.
Yeah, this is a great way to talk about things.
Do you want to just? Would you mind taking us through this?
Actually, this just explains what happens
At t equals zero, do you have one?
I don't have one which
is a
shows the.
Gee, neither do I.
Well, maybe we could. Could we?
But we know what it looks
Could you
like.
sketch it?
Could you sketch it?
Just right.
Yeah. Phyllis, that's. Okay, good.
No, go.
But of course, this now evolves our concept of quantum mechanical states. Each of those lines is a quantum mechanical state, and we can indicate how many atoms are in that state by just drawing a few.
Now, the y-axis there is energy, so we know what's going upwards.
Okay. Yes.
So each one of those states has a successively higher energy as we go up from the bottom of the trap.
And as we cool down, there is less and less energy available, and that means the particles will preferentially occupy lower lying states. And the final state would be, and this is what the Bose condensate is, that almost all the particles are in the lowest state.
Okay.
So this
Yeah.
depicts
That's
the relation
lovely.
between
Wonderful.
energy distribution and
Wonderful.
But there is one difference, and that is what you've described so far would make it seem as though what you're doing is simply reducing the temperature lower and lower and lower and finally getting to absolute zero.
Yeah.
That's not what happens here. What happens is an amazing thing. You lower the temperature and lower the temperature, and then suddenly, at a given temperature, a finite fraction of the atoms start populating the lowest ground state. You still have a distribution up here, but the lowest state develops an extremely high population. For example, there are millions of these states, even very close to the place where the transition takes place. And each one of those states is occupied by a few atoms, 1, 2, maybe 3. When the Bose-Einstein condensation takes place, the ground state, instead of being occupied by 1, 2, or 3, ends up being occupied by 1, 2, or 3% of the entire population. So you can end up with billions of atoms in the ground state. And then the next state up can have 7, maybe 6, 5, something
But I think
like
that is fixable with a number. Just as
It
you
is,
were
but
saying.
it isn't a continuous distribution, it's a phase transition. So instead
Yeah.
of continuously
Yeah.
going to zero,
Yeah.
That's okay.
as
Yeah.
you would if these were,
All
if
these,
these didn't have Bose statistics. If
All
these were
these-
just our conception of a classical atom.
Yes.
They would, the lower the temperature, the more strongly peaked they would be,
That's right.
but still there would be a distribution and it would be smooth. With the Bose-Einstein condensation, you have a smooth distribution and one singular point
Yeah.
at the lowest energy
But
state.
also, yeah, the lowest energy, however, is not zero.
Uh,
That's the key point of the system, really. Were it zero, you'd be in trouble.
Yeah, this
Yeah,
is just the
because we know-
0-point energy we've
That's
talked
right.
about earlier.
That's right.
That's-
It's
yeah,
the
yeah,
last
of course.
little
Yeah.
bit of energy, of motion,
A tiny
left
bit, yes.
at absolute zero.
Okay.
yeah. Now,
So I think,
one of the reasons why this is so lovely for more innocent people is that the image itself very subtly says it can be here and here, but not in between. It gets you thinking
about
in
that
a,
problem.
in a very
And
useful
another
way.
thing which I like about it especially is that a new space has been introduced without even saying very much about it. The
Energy,
space.
exactly.
That's
exactly.
the key thing.
Because you
These don't have to be sitting on a line next to each other. They could be in a triangle, whatever you have in mind.
Okay.
This has nothing to do with where they sit.
Okay.
That's why
So in
I'm
quantum
happy about the
mechanics,
soldiers.
one often speaks about the energy because the energy is a property of one of these states.
Okay.
Whereas position and velocity
Are
or
of-
momentum are not properties of the
They
quantum
can't be sharp
mechanical space.
properties.
And there are
Very
only
important.
some possible energies.
I mean,
Very
this,
important.
this looks so innocent, but it
It's
was
so deep.
in the history of science a revolution. For decades or for centuries, people thought particles are independent. I sort of describe my system by describing each particle. And then, in 1924, when Bose re-derived the Planck radiation law, he sort of treated electromagnetic waves and photons in a peculiar way. It was sort of following that, kind of just putting particles or photons into certain states, and Einstein generalized it to atoms. But what happens in this innocent way is that we are not regarding the particles as independent anymore, but the quantum states, which are indicated here with lines. And this is one of the most revolutionary steps from classical physics to quantum physics, by focusing on states, on discrete quantum states, and not on the particles anymore.
Which goes very strongly to the problem of identity, which is solved only in quantum mechanics.
I was thinking this brings us back to the cover again, because if a very large fraction of the atoms are in the ground state, then they've lost their identity. They're just all in that one state. And here, you can talk about them as being different because they have different energies.
right.
The thousands, millions of atoms that are in the ground state, they're all identical. They're correlated in that if you determine where one is, then that tells you that others may not be nearby. It's a correlated state. They're not independent, but they have lost their individual identities.
So the cover made the attempt, what we drew here as lines, to code it in color.
Yeah.
And the blue color is the lowest line in this diagram.
Yes, but you can't tell that by looking, whereas you can tell that this is some sort, reaching towards some sort of a limit, and you can also tell that there is a distinct difference between what
Yeah.
the different lines represent. And that's so useful to the people who don't know much,
Yes.
because it's a case where an image tells you more than you had to learn. It structures your thinking,
I agree.
and that's lovely.
But your idea of the code is excellent. Seems to me. Then you can use the blue line always to represent the ground state material, and you've solved a lot of problems without even saying so.
Maybe,
You just pick that one out.
maybe.
Say this is the lowest state, here drawn blue. I still worry about the localization, but that's another problem about whether this is the right picture.
I think it's finally starting to seep in a little bit for me, and this is actually quite exciting. The part that is always difficult and is to try to connect it, if necessary, to what we experience in our lives, and we can't with this situation. For whatever reason, people enjoy the metaphor somewhat. That is, it's easier to grasp something if they can connect it with some experience in their lives. And I think in this situation, it's extremely difficult. Unless you have any ideas about that. But yes,
I mean, every kid is familiar with a laser.
okay.
So they know about the optical laser phenomenon. The optical laser phenomenon is also a phenomenon related to indistinguishability of photons and to the wave nature of light. So I
Right.
think we can use I often explain Bose-Einstein condensation as something which is similar to the optical laser. If I want to explain what is the difference between the Bose-Einstein condensate and an ordinary state of atoms, I say it's the same difference between laser light and a light bulb. In laser light, we have all the photons marching in lockstep. We have all the photons occupying the same mode. Mode is the same thing as a state, the same state of the electromagnetic field. And we all know how different, how strikingly different the properties of laser light are as compared to ordinary light. Directional propagation, extreme intensity, can be focused to a pinpoint, and all those properties are now repeated on the atomic level with the Bose-Einstein condensate.
That's
So the Bose-Einstein condensate is for matter what the laser is for light.
And the only difference was that originally the Bose-Einstein condensates did not have a direction associated with them, whereas when one thinks of a laser beam, there's a direction. But Wolfgang has solved that. Wolfgang has made actually a beam of these coherent atoms. So you have a coherent state in a beam, and the analogy is now complete, direct.
But even before that, if you use an analogy in
State
terms of
space.
states and
That's
levels, we are very familiar in physics that there are states where light goes in one direction, or when the light is between two mirrors, the
Right.
light goes back and forth, so it has lost its directionality, and we could even go so far that the light is in a spherical cavity, so it has completely lost its sense of direction, but it is a wave with boundary conditions. So what was a propagating wave, and we know propagating ocean waves, now just becomes a bathtub where some waves are just kind of oscillating back and forth without any direction. So once we accept that waves and propagation is not necessarily connected, a wave is just a state, is a mode, we can make very close connections.
wonderful. Do you feel like going through the process in a minimal kind of way, and actually what you began with and what you wound up with? is it possible to do that in somewhat skimming the surface in a
You mean the atom laser analogy?
Yes.
Or?
No, I'm sorry. The
Forming the condensate.
forming the condensate.
The laser BE analogy, which you just did.
In kind of a series of steps to somewhat take us from a beginning to an end.
Tom knows much more about the beginnings than I.
I don't think that you want historical review.
No, no.
I think you want some idea of how we
But
actually
you-
create
from
these. And hydrogen and the alkalis all start differently. But that's a technical matter, which I don't think is that relevant. But I think once you get to a collection of rather cold atoms, and you can start to do evaporative cooling, then the two are cooled in exactly the same way.
Let's maybe start rather more generally by saying, in principle, to do Bose-Einstein condensation is a very simple experiment. All you have to do is you have to cool down. You have to extract energy from your system. And if you have an atomic system with less and less energy, it means that the Broglie wavelengths, the matter wavelengths get longer and longer. The fuzziness of the atoms gets more and more pronounced. And if we cool sufficiently far down, then those wave packets overlap and they form the condensate. So when we talk about our experiments, and there is a decade-long story, it's just the story, how can you extract energy from an atomic system?
Actually, more than a decade, because Einstein was, 1925? So it's been a long time. And the major problem is that as you cool down any gas, it undergoes a phase transition, but a rather common phase transition. It condenses into a liquid, and then which is very dense. And then if you cool it further, it forms a solid. So you no longer have a gas. You no longer have the opportunity of looking at this. Even helium, which resists condensation into a liquid to the very lowest temperature, you have to go to about 4 degrees Kelvin before you can liquefy it. Even then, it's a liquid, so you can't deal with it as a gas. The system is very strongly interacting, and the real interactions between the particles dominate the subtle statistical mechanical effect that you're looking at here. So the problem was to find a way of keeping the atoms from doing this. And in Wolfgang's case, with the alkalis, it was to work with a gas which remained, well, a vapor, I guess is the right way of putting it, so tenuous that although left for a long period of time, it would condense into a solid. The three-body collisions that were necessary to start forming little droplets just were so rare that they never took place. It turns out that 2 alkali atoms can collide, but there's no way that they can stick together and conserve energy and momentum. It takes 3. And if you bring 3 together, then 2 of them can stick together, stay as a molecule. The third can take away the excess energy and momentum. And then those 2, it's a molecule, it freezes out on the wall. You've lost it. But if, as Wolfgang and others managed to do, they kept the density so low that there were 2-body collisions, yes, you could exchange energy, but the 3-body collisions were so rare that it would take days,
seconds, minutes at least.
Yeah, long period of time, longer than the experimental time that they were looking at, to form a solid, then they could do the experiments.
Maybe what Tom is alluding to is, we have discussed here a fairly paradoxical situation. We've talked about extremely low energy, low temperature properties of a gas. And low temperature means, on the scale of the experiments, microkelvin, millions of a degree Kelvin, or even nanokelvin. So really cold. But now we should ask ourselves, what substance in nature is still gaseous, is a gas at such low temperatures? And the answer is simple, none. There is no matter, as far as we know, which is gaseous at those low temperatures. But now we have these remarkable predictions that a gas at such low temperatures would show wonderful, novel quantum properties. So this seemed to be a certain dilemma. You might formulate it that it's impossible to do it, but to say something is impossible is just a challenge for physicists to
course.
make it possible. And Tom has just explained the way how we could make it possible, namely, if the gas is sufficiently dilute, it takes a long time for the gas that many atoms find each other, form droplets, form molecules, form clusters. So there is a long period where the gas is still gaseous, although at infinite time the atoms would find each other and form higher aggregates. So we can undercool a gas. We can keep a substance gaseous, although thermal equilibrium would require it to freeze to a solid.
Okay. So that turns out to be 1/3 of the problem. The second third of the problem is that if you have the atoms at a very low density, you still have to confine them somehow. And if the atom hits a wall,
Yeah.
then it will stick to the wall. It would adsorb by van der Waals interactions, if nothing else. And you would lose it. It would just stick to the wall. More and more atoms would stick to the wall. They would come together. They would form a solid. Walls are out. You can't have them.
Right.
So the trick here was to form a magnetic trap. All of the atoms that we work with have magnetic moments. And we can trap them in a magnetic potential, a magnetic trap, which does not allow them to reach the walls at all. So that solves...
It's a kind of a suspension. That is just, it just kind of stays there.
It just stays right in
Right
the center
there.
of it.
Yeah, it's magnetic levitation.
Yeah. It's, yes.
Right.
It's floating by magnetic
Right.
forces. So we have atoms floating in a vacuum chamber because magnetic forces compensate, defy gravity.
Not only gravity, because you don't only want to keep them from the bottom of the trap, you want to keep them from the walls as well.
Yes.
So it's a three-dimensional trap.
Yeah.
So that takes care of the problem of keeping them from combining into a solid or a liquid. Then the last third of the problem was, how do you cool it? You have a gas, it's isolated from the walls. How do you get it to a very cold temperature? And once you have it in a trap, then there's a simple technique that you can use. The trap has walls. For example, let's see. Okay. This is meant to indicate, in a one-dimensional way, the trap. You have the minimum energy. The energy rises as you move away from the physical location in the middle of a container. But if you go far enough in one direction, you can go over the edge of the trap. That is, you can actually get out and go to another location, a location where you're no longer magnetically trapped, where you can hit the wall. The atoms that manage to make it to this, this high in energy, if they have enough energy to get over the wall, they then disappear from the trap. But when they do so, they take away an amount of energy equal to the hottest atoms in the trap. So the atoms that are escaping are the very hottest atoms. Then the atoms that remain behind, they still collide with each other, they exchange their energy, and they come to a new equilibrium at a lower temperature.
So that trap is exactly parallel to the trap that they make for themselves when they become a solid or a fluid. When you heat the fluid, the same thing happens.
That's
They
right.
escape the trapping effects and they
Sure,
disappear.
sure. So if we kept the trap barrier at the same height, we would continually get rid of the hottest atoms, but the temperature would get colder and colder, so the atoms would fall deeper and deeper into the trap, and fewer would go out as a function of time. What we did was to slowly lower the barrier in time. Now it turns out, well, we can do that because the barrier is a magnetic barrier. We
Okay,
just turn
so-
down the
oh,
magnetic field at one
gosh.
end of the trap, and the atoms go out. And it turns out
And
that
that doesn't affect what's going on in here?
not if you do it slowly enough. If you ramp down the magnetic field at a rate which is slow compared to the time that it takes the atoms to re-equilibrate, it turns out that for geometrical reasons, there is a relationship between the height of the barrier and the temperature of the atoms that are in the trap. It's about 1/10. So the temperature, or the corresponding energy, is about 1/10 of the energy, or the temperature, that it takes the atoms to escape. So if we drop this by a factor of 2, then the temperature drops by a factor of 2.
Oh, boy.
And we just keep going and going. It works beautifully.
How wonderful.
Well, there was a problem. The problem was that in our trap, we started this with atomic hydrogen. We could only let the atoms out of one end of the trap. And we had a long, narrow trap.
That was just logistic. It was just.
It was just.
You're laughing, but something
That's
was
right.
going on.
That's right. I mean, when people think of long and narrow,
20 years
they think of something like this. Actually, our aspect ratio was 400 to 1. It was a string, basically.
Oh.
And this was only at one end.
Oh.
So this was not a very efficient way of allowing the atoms to evaporate out. What Wolfgang did was to use a different technique. He used an RF magnetic field, a resonance experiment, to flip the spins. Now, since we're by trapping the magnetic moment, if you flip the moment from being up to down, the atom, instead of seeing a confining potential, sees a repulsive potential, and it gets kicked out of the trap. But now, if you do a resonance experiment, if you put on a frequency, an RF frequency, it only resonates with atoms at a very special magnetic field. But that means, since this is a magnetic trap, at a very special position in the trap. So what Wolfgang did was to start his RF frequency at a very high value, which resonated with atoms in the trap at high energy, kicked those out, and then lowered the frequency. And successively, he moved downwards, and here, instead of just letting the atoms out at one end of the trap, there's a killer surface all the way around the trap, everywhere, a two-dimensional surface all the way around, on which the atoms are being kicked out. Much more efficient way of cooling. And that's the way that they got to Bose-Einstein condensation in the alkalis. Of course, we weren't dumb, and after we saw that they had improved our techniques, we used their improved technique, and finally we were able to get there too. So that's of the three problems with getting to Bose-Einstein condensation. There's low density to keep the atoms from condensing into a real liquid or solid. There is the magnetic trapping, keeping them away from the walls. And then there's the evaporation or cooling, which is the way of getting them to the temperature that you need to see the transition.
I think if you want to convey it to people who know very little about science, I think we can explain the evaporative cooling maybe in the language of this magnetic container. We have a box around our atoms, and this box is not made of material, it's made of magnetic fields. If an atom wants to leave the apparatus, it is sent back by magnetic fields. So we should have the notion that we have a box which has magnetic walls. But now by controlling the magnetic fields, we can make the walls of the box soft. And that means energetic particles can penetrate the walls. And this is what Tom was alluding to as a selection evaporation mechanism. The hottest particles can penetrate the walls and can escape. As a result, the atoms which are still in this magnetic box have lower energy than they initially had, because the highest energy particles could penetrate the walls. And as a result, the gas has lower energy and therefore lower temperature. And what was invented by Tom's group was a way to control the strength of the magnetic walls in a very careful way. So by making the walls softer, more penetrable, lower and lower energy particles could escape, and therefore the remaining particles had even lower energy. And this was the key technique to enter micro and nano Kelvin temperatures. So this opened up a new temperature range for physicists
But
to explore.
experimentally, one couldn't do that with the entire surface of the box.
Yes.
We could only do it with one end of the box.
So now we come into technicalities. How do we soften the walls? And the
Well,
traditional
that's
method was
Could we understand that?
that we had magnetic walls and you could soften them only at one point, simply because you were using magnetic fields and superconducting coils to do that. And then there was a new idea which allowed us to soften the walls everywhere, so particles could just escape in all directions.
So it was though you found a way of punching a hole in the box instead of softening it at a given location, all the way around.
This particle is going to escape.
Okay.
I'll be back.
Would we understand what was the advance in the how were you able to have control over, or is that more of a
It was just described. I don't know we want to go into that.
no, but as far as the why wasn't that done before? I guess was it just the idea that wasn't not just. It was as simple as that. I think it's just so logical.
Well, the idea of using evaporative cooling, at least in our experiment, was due to Harold Hess. He was a postdoc with us, and he came up with this idea, and he came to Dan and I. We had reached an impasse in trying to work with the hydrogen.
Yeah.
And he came to us and said, I have an idea. And he explained it to us, and Dan and I just looked at each other and sort of blushed and said, of course, that's a beautiful way of doing it. So we turned around the entire direction, and then eventually we were able to demonstrate the evaporation and cooling.
Yeah.
But I think it's fair to say that ideas were out, and the idea of this evaporation from the whole surface, and it's due to Dave Pritchard and others, and I think it was voiced already in '89. So those ideas were out early on, but the problem is to come to the point that you can implement those ideas. You have to build a whole new machine. So for me, the most critical part in the development towards Bose condensation is that people had to be convinced, had to be optimistic enough about those ideas that they were willing to invest several years of their career, all the resources in equipment and collaborators, and try it out. And this is something which I think is important in physics. There are ideas out, but ideas become real when people vote with their careers, vote with their labs,
But that's what your photograph
to
shows.
implement those ideas.
Yes. Yes.
But I want to point out these are extremely difficult experiments, and just look
This-
at
let-
Wolfgang's apparatus.
I know,
That's what
we
I'm
looked at
telling
it the other day.
This is the thing that gives it away. Each one of these things is a series outcome of some ideas.
Yeah,
That's
exactly.
what it is. But they've got to be turned into wires and pumps and.
Well, what we like as physicists to reduce things to a 1, 2, 3. These were the important concepts. But going
But
from
look,
concept
but,
to making something work.
but look, yeah.
I mean, there were groups all around the world that were working.
Trying to do it. You understand why. It's very hard to do this.
So it takes a team of graduate students 2 years and $500,000 to try out this idea. You
Just
you
to
need
try
a lot
it
of
out.
determination to do
Sure.
it. And so sometimes ideas are around and you can trace them back. And sometimes I'm amazed how few groups pursued this goal. I mean, for decades, your group and the Amsterdam group were almost alone.
Well, there were a few others working on hydrogen too. But yes, they're hard experiments.
But you have to also have incredible confidence in a way to know that you're on the right track. You must have had that sense. Otherwise, you're not going to go blow $500,000 on a
Well,
whim.
there
right?
also have to be some people in the funding agencies that have confidence in it too.
Did you make any? Did you waste any time? Was there a stage where you were heading in a particular direction that? I'm always interested in the errors as well, the miscalculations.
Yeah, most of the time.
Most of the time.
That's right.
It's a generous statement. I
But-
mean, once you figured out how to do it, it
It's
takes most of the time to figure out how to do it, and then to implement the idea which has survived the failures. This is fairly direct. So therefore, once the techniques have been developed, other groups worldwide just take those ideas,
Yeah.
implement them, and that creates a big field.
yeah.
Also in that case, the ideas or the techniques were sufficiently complicated that it took even 2 years for other groups just to copy those methods.
And how is it becoming more refined? I'm assuming it is. As time progresses, do you start editing out certain areas that are not necessary, or do you see
Sure,
it becomes I hate to use the word simpler, but it does in a way. So I guess getting back to where were you able to simplify things that you weren't aware of before? If we could understand, if somebody like myself could understand something like that. Was there an area that you were concentrating on that was unnecessarily time-consuming, for example?
Depends. I mean, for the alkali atoms, things went amazingly smooth. I mean, it was clear in the early 90s that in order to have a major attempt at Bose condensation, you needed an efficient source of atoms, you needed ultra-high vacuum, you needed a magnetic trap, and you had to implement DRF-induced evaporation.
That was a given.
And pretty much this is what we engineered.
Mm-hmm.
I think the only major detour we had is we didn't figure out immediately what the best magnetic trap was. We experimented with different ways of confining atoms magnetically, and this was actually the only point we had to re-engineer.
Mm-hmm.
The other things were just to learn how to master the technology. If you haven't produced ultra-high vacuum in your lab, you can easily waste many months in trying to pump down a chamber, and after weeks you figure out it doesn't work, you have to do it again. So there are many pitfalls, but they are at a lower level. This is just learning the nuts and bolts.
Right.
Yeah.
I thought that there was quite a bit of effort and a lot of maybe false leads in the pre-cooling, the laser pre-cooling. It moved very quickly because there were a lot of very good people working on it. But early on, we, in this discussion, sort of put aside the question of the pre-cooling of the alkalis. But there was quite a race there for a number of years, and the densities and the densities were going up, the temperatures were dropping, as various atomic physics groups, managed to use lasers and Mott traps in one way or another to get atoms to the point where you could begin to do the evaporational cooling. Mm-hmm. It may have gone quickly from Wolfgang's point of view, but it wasn't without a tremendous amount of work and a number of very innovative ideas, I thought. I said, we don't do that, so I can say that looking from aside.
Yes.
But it has, but the work on rubidium, sodium, the alkalis, most of that happened in a period of 3, 4, 5 years.
Mm-hmm.
We started in the early 90s and succeeded already in 95. And there was not too much time to run into completely wrong directions.
Mm-hmm.
But this was something which caught me completely by surprise, because we all knew from the approach in atomic hydrogen, which went on since the late 70s, that it was a decade-long search. And once you go into a new regime of density and temperature, you are in unknown territory. You don't know what is in your way. And I should say, even in the most optimistic days when we try to do that, I felt we are just making one step at a time. I never got euphoric, and I always felt we have decades ahead of us. And that things happened in a few years was completely unanticipated.
Yeah.
It caught everybody by surprise.
But, you know, in the old maps, they said, here there be tigers. Well, now you've got your tiger trapped. And there are two things I want you to tell me. I want you to tell me, what does it tell you, and what do you make it do? What does it do?
I mean, it's funny to think of a tiger, which is an energetic beast, and we are talking about the lowest energy system which nature has given to us. But
Okay.
it's a special tiger, but it has two aspects. One is it is a new window into the quantum world. It has new properties. We have taken all energy out of the system, which means we can see very weak effects, very subtle effects, which cannot be observed at all at higher temperature. So we look at propagation of sound, we look how the whole thing shakes like a piece of jelly, and so we study its properties. But there's also a second aspect, and that is, if we have extracted all the energy, we are really now controlling the quantum state, as Tom put it, or I can say position and velocity to the ultimate degree, to the ultimate extent which is allowed by quantum mechanics. Or in other words, the whole cooling, the production of the Bose condensate gives us ultimate control over atoms. And that's what physics is about. We want to control matter. And we want to control it to learn more about matter, but also to use it for applications. And we are currently considering using such well-controlled matter for precision measurements, to build better atomic clocks, to look at fundamental forces of nature. So this is what we hope the future will bring us.
In exploring the properties of quantum mechanics, as a condensed matter physicist, I'm interested in the behavior of matter in aggregate, where the dynamics of the system, the properties of the system, are determined not by the single particle properties, but the way they interact. And the Bose condensate is very interesting in that regard because of its low density, theorists can do very good calculations which have a high probability of being accurate in a way that they can't do with strongly interacting electron systems. Superconductivity, for example, high temperature superconductivity is still an unsolved problem. Or even closer to this realm, the properties of superfluid helium-4. Helium-4 is a superfluid, has amazing properties. We understand it phenomenologically, but there is no really good microscopic theory of superfluid helium, superfluidity in helium as opposed to superfluidity in the gas, because the system is so dense that the atoms are basically always touching each other. It's a strongly correlated system, and theories are much harder to formulate and to carry out there. So the Bose gases give the theorists now a wonderful opportunity of looking at interacting systems in a way where they feel that their theories are both accurate and computable.
I mean, it is an amazing world. At some point, we looked at our gas, the Bose condensate, in the magnetic container. And what we saw caught us completely by surprise. We saw that the system had layers where the orientation of the atom was alternating. This looks like sort of an, layered cake. I mean, it's something we are very familiar with in the world of condensed matter physics. You can stack different materials and they stay put. But for a gas, a system which is 100,000 times more dilute than the air around us, you would not expect that a gas can be stacked in layers. In other words, what it dramatically tells us is that we are at densities which are 10 to the 800 million times lower in density than the ordinary condensed matter state. But we are observing phenomena, ordering, stacking, miscibility, immiscibility, which have been studied so far only in condensed matter systems, in liquids and solids.
But that's, of course, the paradox of the name.
Yes,
Like, this is a condensate that is not condensed
Yes.
in the ordinary sense.
yes.
It is not dense.
But it has the properties of condensed matter systems.
It has-
We are 100
because the
million times.
complementary variable is just as good as the one that isn't.
Yes, we have
Remember
100,
space
we have
is
100
space.
million times lower density, so all those forces which create ordering and other
Don't
things
matter.
are much, much weaker. But we are at an energy scale, temperature scale, which is 100 million times lower.
Right.
So that
Well
means
said.
we can observe truly generic condensed matter phenomena at extremely low
That's very
density.
good, yes.
And the description of matter at ultra low density is much, much simpler. If the atoms are not squeezed against each other, we don't have to understand the complicated things which happen in the proximity of an atom. We only sort of need to know the simple physics which happens at long range. So therefore we hope that we have now the tools to quantum engineer condensed matter systems and understand them in great detail, and learn something which we hope is very general about nature.
We should remember that this only applies to half of the atoms, because this only applies to atoms which are bosons. the other fraction of the atoms obey a different kind of statistics, Fermi statistics. And this phenomenon just doesn't occur. Because as you go to low temperatures, instead of allowing many of the atoms to condense into each one of these states, there can be only one atom in each one of the states. So instead of at T equals 0, all the atoms in the bottom state, at T equals 0, there's 1, and then 1, and then 1, and then 1, until you go up to a total number of states equal to the total number of atoms. Each one has its own individual state.
Oh, God.
And Bose-Einstein condensation doesn't occur in that system.
But that system will be cracked.
That's
too.
Oh, yes,
Yeah, that's the metal, or the ice, or whatever you have in mind.
This is a detail question, but I'm always interested in what happens at interfaces. Is there something when the strata, if I could use that word, at the very interface, is there something happening there at the boundaries?
Of that?
I have it on my computer. I don't have it in this stack of printouts, but
Could you-
there's a picture which shows the following. If we have the magnetically, let me just illustrate if you feel
See.
lines. When we take this magnetically confined
Well,
sample,
yeah, use that.
and then switch off the magnetic container that the system flies apart, we saw pictures which just showed a regular array of striations.
Right.
And because we knew what has happened between here and there, we knew that the system in the magnetic container consisted of alternating layers of two different quantum states. So it was like a stack of alternating layers of two different materials.
And what was different? The spin orientation?
It was a spin orientation. So it
That's
is
all they
magnetic
have left to be
domains.
different.
But and again, maybe I'm thinking more about the material world, but what exactly happens at that boundary? If you're
It is
demarcating,
exactly, you can imagine it, it is as if you would carefully pour vinegar
Yeah.
into a beaker and then add oil to it and you have a layer, add vinegar again and you don't stir it, you're just very careful. You would create alternating layers of oil and vinegar.
I do understand that, but at the very boundary between the oil and the vinegar, something molecularly is happening. And
Okay,
I'm
this
just,
is now different in the gas. What happens is, what is a sharp boundary between oil and vinegar is a soft boundary. So I would actually,
Okay, that's
if I
actually-
would draw the density distribution, I would draw it in this way, which would mean this is kind of our quantum oil, quantum vinegar, quantum oil, quantum vinegar, but because it is a gas, they overlap.
okay.
And this overlap is enforced by quantum mechanics because an extremely sharp boundary, an abrupt change in the quantum mechanical wave function costs energy. So therefore, the system can lower its energy by somewhat penetrating into each other.
Okay,
So this is again quantum mechanics at work.
I see. Is that an interesting place for you, this place here? Are you interested? I mean, are things going on here that are different from here and here that could be interesting?
Yeah.
It's a different, unless I'm misunderstanding, it's different from these two.
Sure, there are
It's a
different
third,
things happening.
yeah,
The
and so,
unusual collisions will be
so
different.
could
You
it,
don't have
could it,
much.
it's just a question about, because I have a chemistry orientation, because that's where very interesting things happen in chemistry. And I'm just wondering if there's a similar situation.
I think that probably depends on the interactions, on the collisions, because the separation mechanism, the reason that this doesn't go sharply to zero is a quantum mechanical reason. You can't have the wave function drop rapidly to zero unless you put in more energy. So even with no interactions, you would have this overlap. The interfacial phenomena that we're familiar with in chemistry and physics usually happen because of an interaction between the two different systems on either
Yes.
side.
I see.
Interactions are quite weak in these Bose condensates. Not zero, and certainly Wolfgang has seen lots of effects of the interactions, but they don't dominate usually the system. So I think that's why it's a little hard for us to answer your question. Probably there are interesting things that are going on there. We may not be able to see them yet.
But just to guide your imagination, what is the density and what makes an interface between two gases? The density of the material is 100,000 times less than the density of air. So it's almost nothing.
Yeah.
But we can see it with the methods of atomic physics. So if you would imagine I take a microscope and look at the interface.
No.
you're dead wrong.
No. That I know.
We use
That I know.
extremely
I promise.
sensitive methods to sort of see those structures.
Yes.
And so far, I should say, we couldn't really resolve the
Yes.
interface region well because it is comparable to the optical resolution.
Yes.
So we have seen this interface only indirectly. When the whole system spreads out, we saw those magnified layers, and we could, to some extent, we used atomic motion to magnify because we couldn't see it directly. We are currently trying in experiments we are setting up to see those structures more directly. But what we have used so far is we have used the atomic motion that things just burst, ballistically expand. We have used that as a tool to magnify the structures, and then we could readily see them. So this is sort of, for me, the most striking example that we are doing condensed matter physics in a regime which was unheard of.
Yeah.
Let me give you another example. In solid-state physics, one often has a magnetic system which supports spin waves. For example, if you have a ferromagnet or an antiferromagnet, where you have a solid, there are magnetic moments on the individual atomic sites, and they may, if you tweak the system, you can get a spin wave so that the spins will oscillate in direction, up, down, as you move along the sample. The reason that that wave exists, the reason you have a restoring force, is that the wave function of the electrons on one atom overlap the wave function of the atoms on another. So it's natural to say, sure, a spin wave, of course, if I flip the spin on one atom, it's going to affect the neighboring atom. No problem. And spin waves exist, and we've seen them for a long time. In the process of trying to get atomic hydrogen colder and colder, we reached a place where we had some very cold hydrogen, but not cold enough to Bose condense. And a group at Cornell University did an experiment where they saw spin waves in this gas of atomic hydrogen. And the interesting thing about those spin waves was that the atoms were about at least 1,000 times their mean diameter apart. It was an extremely low density gas. But there was a spin wave, a beautifully well-defined, very sharply detected. In a magnetic resonance experiment, you could see this thing extremely clearly, beautifully well-defined. But the atoms were 1,000 times apart compared to their own distance. And this collective wave in the spins existed. And it's because of quantum mechanics. And it was just, again, a very beautiful example of a cooperative phenomena in an extremely low-density system. I wish we had done those experiments. We didn't.
You can probably apply to this the phrase which was used in a different context of spooky action at a distance. Sort of quantum mechanics is a little bit spooky. Things happen at a distance where normally things would not happen.
Yeah.
And the spin waves in an ultra-dilute gas of hydrogen are a nice example that quantum mechanics has different scales as we would usually associate.
That's hard to grasp as well. Scale. It's always difficult.
Well, localization is a fragile thing. We think of localization as being, everything must be localizable.
Yeah.
But it's not true.
Yeah. Yeah.
Yes.
And that's the thing.
That's okay. What time is it? Someone?
10:35.
I think there's a lot of material here. I think that
I think there's some good stuff, yeah.
wonderful conversation. It's interesting. It headed in a completely different direction. I wonder if we all had an idea of how this conversation was going to. I imagined you drawing for me all these wonderful things, and yet And you did, yeah, drawing in other ways. Any final questions that we would think we need clarity or?
There was the business of the dot of the eye. Tell us about the dot of the eye.
It's
Well,
a
that's just a way of extrapolating
Yeah,
what you said.
but
it's-
no, it's an example of an explanation,
I would like to
which
hear it.
because it connects to
I'm
experience.
trying to describe the weight of the BEC. And I said, well, it's like this. A period of ink on the paper is pretty small and not very heavy, you would believe that. If you took a very good microscope, which you don't have, and could somehow draw 1,000 lines on it this way, and 1,000 lines across it this way, and took one of those pieces, that would be 100 times the weight of the Bose-Einstein condensate. I think I'm right about that.
A millionth of the dot of an eye is
The weight of a
still.
Bose condensate is about 1 femtogram. So,
A tenth of a gram?
a femto.
Femto.
Oh, a femtogram, yeah, sure. That's 10 to the minus 14 is not so far off that.
okay.
Yeah, that was roughly.
Can't even conceive.
But
But it just gives some feeling. to
Sense
people.
of scale.
But it's things like that that are so easy an argument to follow. You're not frightened of it. You're not required to go through so many steps that
so
you
sure
can't
about
follow.
this, but-
And you're left with an image which you then use as you listen to the next steps.
Yeah.
Well, of course, the Bose-Einstein condensate does fall under gravity, and if you let it out of the trap, you have some pictures of
That's
condensates
wonderful,
dropping
yes.
in
Oh, yeah, that's very light.
Tremendous.
It's really the most refined chemistry that was ever done on sodium. Or anything else, probably. I mean, there's no sample like that.
That's true.
That's the first thing you said. But you call it a condensate. Well, because it is, but it's such a different one.
Yeah.
That's what, when I first wrote to you, I said, can you talk to me about, the word condensate? Is that the right word?
No, it's not the right word, but
For us
they're
to
stuck
try-
with
It's a
it.
very dramatic word.
Yeah.
We did that in one of his
I think it is, and I mean, this is a slide I've shown often. I said condensation is droplet formation.
Yes,
This is
okay.
what we associate
Yes,
in
very good.
everyday's life, but it is a weird droplet in a weird vapor, and the weirdness is the quantum weirdness. But I mean, these are real data. What it depicts is it's false color coding. Green means low density, red means high density. But what you see is this elongated gaseous cloud, and it's elongated because our magnetic container is cylindrically shaped. And now we cool down. A gas which is cooled down shrinks, and you sort of see how the wings of this distribution shrink. It gets colder, and the gas is kind of more concentrated at the bottom of the puddle. That's what cooling is about. But then you see at a very well-defined point, all of a sudden,
Yeah.
color-coded in red, there is a droplet. There's a high-density phase. And this droplet is the Bose condensate. So somehow this looks very similar. If you look at a vapor, you cool it down, and you reach the onset of condensation, and then droplets appear in the vapor. But the droplet is a quantum mechanical state, the Bose condensate, and the vapor is not saturated because it has reached a saturated vapor in the ordinary sense, but in the sense which Tom mentioned, it's a quantum statistical sense, it is quantum saturated. And it would be difficult to explain what that means, but just the analogy with a vapor which cools down and droplets appear, this is what we visually see when we look into our magnetic container.
I found this image very mysterious. I'm delighted you just told me that.
By the way, the suddenness, you said, you used that word, that point in time when that happens, gives you information. If it happened another time, it would mean something else. Is that fair to say? The fact that it's happening at that time is giving
I
you.
think it's not
happening
time
at that
which is important.
temperature.
The controlling
temperature.
parameter is the density, actually, in this case. When you hit a critical density in the bottom of the trap, then this begins to form.
would it be the same with any alkali? Is the same density? Is the density dependent?
There is a predicted scaling with the mass and the properties of the atom. Or it's actually only the mass.
That's right.
But the suddenness is sort of really striking. I mean, imagine you see a system which slowly gets colder, 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 and all of a sudden something happens. I mean, if you would cool down the air in this room, it gets colder, sure. You start freezing. It gets even colder. But all of a sudden, liquid air appears. And this is what Tom described as the phase transition.
Yeah.
A sudden change in the physical properties. And this suddenness depends only on temperature and density.
That's all.
Yes. Whenever we bring a system down to the same temperature and the same density, exactly the same thing happens.
Mm-hmm.
It defines a phase transition line of density versus
Okay.
temperature. And if one cools down at different densities, you hit this at different temperatures.
Yeah.
And by mapping out the way the density varies as a function of temperature, you measure the phase transition line just as you would in any other phase transition.
Mm-hmm.
And that was one of the signatures, that this was, in fact, Bose-Einstein condensation and not something else.
Mm-hmm.
Nice.
Wonderful. Thank you.
Okay.